electronegativity is the last property that you can that we're going to discuss, that can also be inferred from the position of an element in the periodic table. And electronegativity is an invented scale. Pauling developed the scale that we use nowadays. It's a measure of how strongly an atom attracts a pair of electrons, sorry, I said here, chair, a pair of electrons when forming a bond. So this is, the atoms have already made a bond. Let's talk about our friends A, another atom called X, and they're making a bond. And that bond is a covalent bond. The electrons are being shared. Nobody has given away the electrons to nobody. They're both sharing them. Sharing doesn't mean equally sharing. One can be stronger than the other in attracting those electrons from the bond. So yes, they are being shared, but they spend more time near one of the atoms, closer to that nucleus, to the nucleus of one of the atoms. And that's what electronegativity tells you. How strong an atom is to attract the pair of electrons of a bond when it's forming a bond with another atom. It's affected by the size of the atom, and that sounds reasonable. How far are those electrons from the nucleus that is attracting them? So if you have a very large nucleus, if you have a very large atom and the nucleus is in the middle and the electrons that are being shared are in the outer shell, they're going to be very far away than if you have a much smaller atom in which those electrons being shared, they are closer to the nucleus. And it also depends on the atomic number. So how strong is that positive charge? How positively charged that nucleus is, how strong it is to attract the electrons from the bond. So how small it is, the smaller it is, the closer those electrons will be to that nucleus, the stronger it will be able to attract them, and how strong that positive charge is. Because the higher the mass number, the higher the atomic number, the more stronger that positive charge is, the stronger it is to attract it. So electronegativity increases as we go up the group because the atoms become smaller. So if the atom is smaller, it will be much more able to attract those electrons that it's sharing with another atom. And electronegativity increases as we go towards the right in the periodic table. Again, atoms are smaller within the same period. Atoms become smaller as we go towards the right. So those atoms in the same period, if you compare nitrogen and oxygen, well, oxygen is smaller than nitrogen, so it's more able to, those electrons in the bond will be closer to the nucleus of oxygen, and oxygen would have more tendency to attract them. Again, hydrogen and helium, because they're so small and because helium doesn't react, doesn't have any compounds whatsoever, are out of the equation. So the most electronegative atom of the whole periodic table is fluorine. In a competition for electrons in a bond, fluorine always wins. So if you have a nitrogen and an oxygen attached, oxygen will be stronger than nitrogen, attracting those electrons from the bond, and it will be able to pull from those electrons from the bond. They are being shared between both atoms, but they will spend more time under the sphere of influence of the oxygen. However, if you have a bond between an oxygen and fluorine, fluorine is smaller than oxygen, and it's stronger attracting the electrons from that bond. So those electrons will spend more time under the sphere of influence of that fluorine nucleus. So and we put those arrows to try to signify that, who is pulling away from the electrons. They are being shared, but they are more in control of one of the atoms than not the others. And then you have sometimes when you have, for example, a compound in which all the atoms are the same. Well, if you have, for example, an atom of oxygen attached to another atom of oxygen, then, they both have the same strength. So none of them is a winner when attracting those electrons. So why care about electronegativity? Well, because in chemistry, because we're all about electrons, because we're all about making bonds and breaking bonds, it tells us who controls electrons in a compound. So you have different atoms, and all those atoms have a different electronegativity because they have a different strength of nucleus and they have a different size. Who is controlling the electrons? Where are in that electronic cloud surrounded surrounding those atoms? Whereabouts the electrons are in the molecule? How vulnerable is that bond to be attacked? Because if the bond is very skewed towards one of the atoms, if those electrons spend a lot of time around one of the atoms and not the other, then you're creating an imbalance in the charge. They're not evenly distributed. You have a section of your molecule with more electrons that has a negative charge, and a section of your molecule with fewer electrons, and it gets a sort of positive charge. And more specifically, when a bond is broken, which atom will walk away with electrons? So if I have, for example, hydrogen and a chlorine, hydrogen is well towards the left of the periodic table, chlorine is well towards the right of the periodic table. It's more electronegative than chlorine. And despite the fact that hydrogen is very small, again, it has a huge tendency, because it's so small, it has a huge tendency to not control the electrons. So the electrons in that bond are polarized, are skewed towards spending more time across the chlorine. And when the bond breaks, you will actually have a situation. It's okay while they are together, it's fine. Okay, so one controls the electrons more than the other, so be it. But the point is that when that bond is broken, then the one that is going to walk away with electrons will be the chlorine, its own electron, the one that has taken away from the hydrogen, and the hydrogen will be left without that electron. So that's why we care about electronegativity. It tells us at any given time, if you look at a molecule, where is the maximum concentration of electronic charge? Where are most of those electrons in that compound? Who controls them? And when the bonds break, who is going to walk away with electrons? So this was all for this series of videos. We have been covering some key concepts about atomic structure, what's an orbital, energy levels, and very importantly, atomic number, mass number, and isotopes, and also atomic mass. We've been looking at how we can use atomic number and mass number to tell us, to determine how many protons, electrons, and neutrons an atom has. We've looked a bit about what the periodic table is, why it is structured the way it's structured, why the elements are in the places where they are, and what sort of information it can give us, and how you can use the position of an element in a periodic table to predict some characteristics of how it's going to behave. The size is going to be, the ionization energy, how is it going to be for that atom to become positively charged, the electronic affinity, how easy it is for that atom to become negatively charged, and electronegativity. If that atom is making a bond with another atom, which one will be in control of the electrons? So this is all from me for this series of videos. I hope they were helpful. If you have any questions, as usual, just drop me an email. And thank you very much for watching.